Yeah, so this is stuff that Jim and I are actively working on. This has been coded recently and everything, so you'll be the first to get a go at trying to use it. And so this is related to stuff that I did do for my PhD, which was more on inference of Markov chains of various orders and applying it to coarse-grained dynamical systems. Here we're trying to push it to something which is applicable to computational mechanics, where the states are potentially hidden. And one of the big issues was, how do you get to that when the observed data is not necessarily directly reflecting the observed data is not reflecting in a direct way the internal states of the machine that might be the correct one. And so I'm going to take a slightly different, my goals are very similar to what you've been hearing in the previous 2 quarters, but it's going to be from a very different viewpoint in a certain sense. So hopefully some of the language I'll use is very similar and might be confusing. I'll try and be very clear about what I mean in this case. If it's not clear, then ask. So let's see. The basic overview of what I'm going to do is today I'm going to talk about just general goals in my view of statistical inference. What are we trying to do? And in particular, a Bayesian approach to the problem. And I'm going to do a couple of examples. One is for a biased coin, just inferring the transition probabilities. And the next will be moving on to epsilon machine-like structures, so unifilar hidden Markov models. So not all hidden Markov models, just unifilar ones. And that actually turns out to be very important. And I'll do an example of something called the even-odd process, which is like the even process that you've seen, but slightly more complicated. And all of today we're going to be focused on, you have data and you have a known structure. You just want to infer transition probabilities. So what I mean by known structure is you know that there are a certain number of states, going from state A to state B, emits a 1, but you don't know with what probability. So it's going to be figuring out what are those transition probabilities, and in the case of something where there are hidden states, what is the actual hidden state dynamics? What paths did it take through the machine? So we actually need to figure that out to infer these transition probabilities. And then the next lecture is going to be on how do you actually then differentiate, given a certain data set, between structure A, structure B, and structure C. And the approach that I have been working on is using Bayesian methods for model comparison and work by Ben Johnson, who had a way to enumerate unifilar hidden Markov models, or topological epsilon machines in this case, which are more restricted than all unifilar hidden Markov models. But in general, just let's try everything, pretty much. Enumerate all possible structures, and then for a given data set, which is the most likely, which is impossible, these kinds of things. And so, of course, this is limited by computational power and all these kind of things. But actually, I think you can get quite far doing that. And so there I'll be doing 2 examples, or one example in particular. I'll be doing the even-odd process. But in that case, what I'll be doing is not assuming a known structure. I'll be just saying, give me the data, and then I'll throw thousands of different topologies at it and see which is the right one and see if we can actually figure it out. And then example 4 is going to be, I'll do a survey of processes that you already know, golden mean, even, and the SNS, which actually in this case will be out of class because that's non-unifilar. And so this will be more the kind of the stuff that's going into the paper that we're working on. So it'll be fancier plots, these kind of things. So you can get a sense of how all this works. And I'll wrap up with some complications in terms of motivated by the SNS. How do you think about out-of-class things that aren't unifilar hidden Markov models? And also, in real data, things might be non-stationary. How might you approach that kind of thing? So just kind of gotcha kind of things. And partially the way that I've done this is I've tried to make it, there's code in Campy that does all of these things. So the slides here, there'll be Python code in there. And this is actively run and put on the slides. And the lab that you have on Sage goes through all of the examples exactly. So you can play around with this stuff afterwards. So that's really a big part of the goal, is play around with this afterwards. OK, so that's the outline. Let's get started. And so partly I've already been describing this, but I'll just sort of introduce some of the notation and divide how we're doing things. So the first level, again, is today, which is you're going to be a given set of data, which I'll just generally use D as D. We're going to infer parameters, which in statistical inference is often used a theta, and this can be one or more parameters. It's very non-specific. And I put these little index i's, which is sort of a reminder that we've chosen a particular model I. Okay, so that's all that it's meant to mean, is that we're using this for a particular structure. So this could be like, we've assumed a Gaussian, that's our model I, but in this case we'll assume a particular topology. And again, M is the actual model itself, so a particular model has a certain set of parameters. Okay, and so today we're going to be, two goals is provide a point estimate of parameters. So that's the idea is, the transition probabilities are, 20% this way, 80% that way. So you get a particular number. But with finite data, everything is always uncertain. So that's only half of the story. The other part is to quantify the uncertainty in the estimate. So actually, your transition probability might be, your estimate would be 10%, but it might be between 3% and 15%, with 95% what in Bayesian lingo would be called a credible interval. So we'll say, what is the possible range of values for this parameter given we had 1,000 symbols, this kind of thing. And so that will be for today, and then we'll go into this comparing of many models, and then again it will be a single data set, but now we'll be considering a whole bunch of models from some set. And so the examples from Thursday will be topological epsilon machines with 1, 2, 3, 4, 5 states. So it turns out that those are around 38,000 topologies, and we'll be using this a lot. And I'll describe that next time. Sort of the numbers are quite impressive, but you can actually throw a lot of computer power at this and get some interesting results. And the other thing is that you will always get some results, or at least you'll get results that have some topologies that will be consistent with the data, which is kind of a surprising thing, at least for me. I didn't expect this, but stay tuned for next lecture, is that it turns out for even things like the even process, when you throw this at the library, there'll be hundreds or thousands of topologies that will say even process could have come from this, and we'll sort of explain why that's the case. And here then we get this extra level of what is the uncertainty in the model structure. So we end up with probabilities of a particular model structure given the data and the set that we've looked at. But the most likely one may only have 5% probability. So then you're very uncertain what the actual structure is. Or it could have 99.99999% probability. And those are very, very different things. So I'll also discuss how to think about this, because what I think a lot of people want to do is, here's my data, give me back a single model with very specific transition probabilities. And I'm going to argue that sometimes will be okay, and other times will be disastrously wrong. So you just need to be careful about, in particular, what this distribution over models is given the data. And then the final thing, because we spent a lot of time learning about computational mechanics and information theory, we want to estimate some of these quantities that you learned about. So C mu and H mu. And all of these are functions of transition probabilities, which with finite data are uncertain. So your estimates of H mu and C mu and every other thing are going to be uncertain as well. So I'm going to argue for this sampling approach to estimating sort of averages of these quantities, and again, credible intervals for these quantities that are a function of how much data you have, what models you're using, and all this kind of thing. So that's the big overview. Let's get into it. And for this first part, I'm going to be sort of building up the theory and introducing notation. So I think we've gone most through all the notation here. And so our goal at this first level here is to come up with this thing we call the posterior distribution, what is basically the probability density of the parameters given the data and the model. And so this really is a probability density over the transition probabilities. So this is something that you can integrate over and will be 1. This is part of why we can sample from it. But how do we get there? We have to build up things that you're probably familiar with in terms of a likelihood. We're going to have to define something that's a prior, which is often more mysterious if you haven't done Bayesian kind of things. And one important thing to keep in note is this prior that we do have to choose is something that will affect what we get out here. So how you set the prior is actually important. You can set it very weakly and have it not affect what the posterior says, or you can set it very, very strongly and have very erroneous conclusions. So part of the goal will be to figure out what does your prior say, how much is the data contributing to it, and do this all in a reasonable way. Okay. So these are the basic elements at this first level, and I'll go through all of these very specifically for the biased coin example. And so the first is going to be the probability of the data given parameter settings and the model. And so actually this is very similar to the kinds of things that you've already been calculating, is that you know the transition probabilities. What is the probability that you saw a 0, 0, 0, 1, 1, 1? So basically it's that kind of thing, except in this context we're often thinking of this as we write down that probability, but we really don't know what the transition probabilities are. We can write it down and say that it's p to the 0 with a number of zeros in the word, and p to the 1 with a number of ones, but we don't know what they are, what the transition probabilities are. And then the other part is this prior, and this is something about prior assumptions, expert knowledge. It could be restrictions. I mean, if you're actually applying this to a physical system or social system, something, there might be reasons where you would say that I think that these parameters should be between thus and thus. The way that the Campy code is set up and the way that I generally approach these things is to set everything really diffusely and just let the data drive it. But this is something to be considered, and I don't think it's necessarily a bad thing to use if you really have the grounding for it. And the other way to think about it is that if you have two data sets, your prior for the second data set could actually be the posterior from the first set. So it could be something that's informed by, you can add chunks of data and keep updating. And then this quantity here is something called the evidence, and actually turns out to be, we're going to see this over and over again, and it turns out to be just, it looks like a normalization constant in Bayes' theorem, but it's a probability of the data given the model, and so it's very close to the likelihood, but what you end up doing is averaging over the uncertainty in your knowledge of the parameters. And so it's something about the probability of data just given the model with taking into account that we are uncertain about the model parameters. And this will allow us to actually do model comparison at various levels. So we're going to have terms like this that will come up over and over again as we do model comparison, first for transition probabilities, then inferring start state, and then looking at different model topologies. There will be terms that are like this. So just a heads up to pay attention to that. And so all three of these things go in, well, basically these two things determine this, and then you renormalize and you get a posterior, which is very much like a prior, but now it's now conditioned on the data. So we've integrated the data and prior assumptions. All right. So the basics of Bayes' theorem is this creature right here. And so the posterior is what we want. We have our prior, the likelihood, and then we have this evidence term. So like I said, the evidence term looks like a normalization constant. And the form of this depends, again, on whether or not these theta I, which is, again, a loose term for just whatever our parameters of interest are. For transition probabilities, these are going to be continuous. And this evidence will actually be an integral of the product of the likelihood and the prior. Whereas if it's discrete, for instance, trying to figure out what state our machine started in, it will be something that looks like this, where we iterate over the discrete choices of it could have been in start state A, B, C, or D before it generated the data we saw. So this is a very general form for Bayes' theorem, and the normalization just depends on what types of parameters we're dealing with. All right. So the biased coin. So all this kind of stuff, when it looks in kind of typeset, this is actual Python code in Campy. So when you go to Sage and look at the notebooks, all this stuff will pretty much be verbatim there. So you can play around with it and get a sense of it. And I chose the biased coin as a particular, I think it seems like a trivial example, but it lets us get used to inference. But also we can think of this, and the way that I defined this in Campy was to make a string and then put that string to the Campy machines from string. And so I made it actually into a recurrent epsilon machine within Campy. And so this is just like the even process or random XOR. It's something with a state and has edges. Okay, so I'm going to use this extra notation that looks extraneous when I'm doing the biased coin, but it's because that carries over to all of these other things. And so I also chose a biased coin rather than a fair coin because the prior will, without any data, the default setting will on average be the fair coin. And so I wanted to be clear that we're not just sort of getting back what we're getting from the prior. So that we're having something that has 10% probability of producing a 0, 90% probability of producing a 1, and it always goes back. And the key to inferring probabilities is really going to be how many times did we take this edge? How many times did we take this edge versus how many times we were in this state? And this carries over to the even process also, is that we're going to be how many times we were in state A and we took a 0 and came back versus how many times we were in state A and did a 1 and went to state B. So it's exactly the same thing. So this can be seen as you're going to have basically a binomial distribution at each state. And each state will be a binomial distribution. So this completely carries over. It's just you end up getting products of these things. So it's a good place to start. And less trivial than it might seem at first, but it lets you do everything. So let's assume that we're assuming this model class, we have some data, and we can write down the likelihood. And so this is what I was saying, and that this is something very familiar to what you've already done before, is that if we looked at the data, the number of times we saw Q0 and the number of times we saw Q1, we could basically just count from D. Like Q is not really important here. That's why I mean the notation is overly specific. But it's the number of times we saw 0 in the data set D, and it's the number of times we saw 1 in the data set D. And that's also the number of times we traveled on those edges. Again, we're assuming that we don't know what these things are. We're going to infer them. But we can write this down in principle, and the likelihood for these things that are fixed from the data, what they would be. And so if you wanted to do maximum likelihood kind of things and estimate probability there, you could actually just maximize this thing. Treat this as a function of the model parameters. And often you take the log of this, maximize that, and you'll get the maximum likelihood estimation, which would be just the number of times you've seen Q0 over the number of times you've seen Q. So very, very straightforward. But we're going to add to this and use the Bayesian machinery. So again, just being specific about the notation, MI is we've assumed this single state binary machine. The unknown parameters are these two transition probabilities. And of course, they're constrained to sum to 1. And the data is these two things. And as I've been saying, think of these things as edge counts, because that will be important later. All right. So then we get to the prior. This is the next element of Bayes' theorem. And so it turns out this particular form, like this particular form of binomial or multinomial, so it doesn't matter that we're doing 2 letters in our alphabet. It could be 3 or 10. It could be any number. So this is completely general. There's what's called a conjugate prior. And for just binary alphabets, you can think of this as a binomial distribution, and the prior that's conjugate will be a beta distribution. If you have more than two letters, there'll be a multinomial version, and the prior will be Dirichlet. And what it means to be a conjugate prior is that if we assume the prior of this form, our posterior will also be of this form. Okay, so we'll end up getting a posterior that looks exactly like this, but where we have these alphas will be now alphas plus data that we've seen. So then that actually helps in terms of what do we think of this alpha. So the first thing is that this is actually a probability density over these parameters. So here you can see actually the restriction that they have to sum to 1. So it's actually on the simplex. You have this factor here, which is the probabilities to these alphas. And the alphas are parameters that you set. So these are parameters for the prior. And in practice, and in the way that Campy handles all this, these are set to 1. And what that ends up happening is that the transition probabilities end up being uniform over the simplex. So your expectation is going to be 1 over the number, the alphabet size, but that will be only the expectation. You can see any value between 0 and 1 subject to the constraint that they sum to 1. And we'll sample from the prior to show you that this is what's going on, which is good to understand. And then this term here is actually just a normalization. So you can literally integrate over these probabilities and get 1. Okay. And so I guess the last thing is this term here is the sum over each of the edges. So you can see that there's a qx, which is kind of the alpha parameter for the edge q0 and q1. And you can think of these as artificial counts. So by setting 1, it's basically we said we've given 1 count to this edge and 1 count to that edge. And sometimes people who don't like to do Bayesian things will call this smoothing. But I mean, really, and for small data sets, it's important where you might get a maximum likelihood estimate of 0 probability for something, but you don't really think that. And so partially this is what this is doing. And then we also have a counterpart to the number of times we've seen a particular state, which is this thing where we sum over all outgoing edges. And so this is a value of 2 in this case. And of course, this depends on the size of the alphabet and how many edges you have on a state, these kind of things. And the way to think about how much the prior is saying about what you're inferring versus the data is to compare these values of the edge prior relative to the number of times you've actually seen it. So if you've never actually seen any traversals on the edge, your estimate is completely prior based. Whereas if you see some traversals on the edges, it will be basically the number of Q0 versus the alpha Q0. So if the number of times you've done a 0 is 1,000 and you've set alpha to 1, basically the data is driving it. And there'll be no difference between the maximum likelihood and the posterior estimates. It does become important when there's small data, and that's where I think everything becomes really important. And priors are sensible, and you know what you're setting. So I'll argue that it's a good thing to do, and that you can understand what it's doing relative to the data.
Sorry, where are those equations from?
Where are these from?
Yeah. Is it written in any proof textbooks or
Yeah.
or which textbooks?
So like Wilkes statistical mathematical statistics, so Dirichlet and multinomial distributions are well known. Yeah.
I don't understand anything.
Well, okay. I mean, I'll give you a sense of what it is. I mean, the way to think about it is that it's a probability density over PQ of 1 given Q and 0 given Q, and this is constraining it to be summed to 1, and it's done in such a way that when you integrate over this thing with respect to 1 given Q and 0 given Q subject to them summing to 1, that you're going to get back a normalized distribution that will be have probability 1. So it's just a probability density. It's a probability density of probabilities, which is kind of a weird thing, but it comes up in machine learning a lot because of that, because you're often trying to infer probabilities. And so multinomials and binomials will come up, and then their counterpart to betas and Dirichlet's. So I mean, another question is, I don't have to choose the conjugate prior, right? I could choose any prior that I wanted to. I think this is a sensible one, and then it's very flexible in terms of setting things. I could set this, I can set alpha Q0 and alpha Q1 and change the shape of my prior. So when I set these to 1, it's flat over the simplex. But if I set each of these to 1,000, my prior mean would be still 50-50, but it'd be sharply peaked, and it would take huge amounts of data to differentiate between that. But the advantage of these kind of things is that with this, because it's a conjugate prior, I'll end up with something that is also a beta or Dirichlet. And so things like averages of these things and all moments of these things are analytically calculable. And that's really, so I don't have to do any sort of numerics to figure these things out. I can just write them down and use them. Yes.
So ultimately, you're just looking for 2 numbers out of this, right?
In this case, yeah.
So it's
Or 1, really.
A lot of ink to get 2 numbers out.
Well, okay. So I mean, I could have done this. Yeah.
But I mean,
Yeah.
To paraphrase what I think you're saying,
Yeah.
is you're arguing that the motivation for using this particular form is that it allows you to make interpretive statements about what the prior the values assigned to the priors themselves as mean.
Yeah,
They're physical in nature.
they're easy to understand. And also I think that, I thought about doing an example where you had an alphabet of size 20 and you're given 10 samples. Things like this. So Bayesian methods using this stuff would still have sensible things to say about this. It would give you means. It would say everything is completely uncertain. It's dominated by the prior, but it would still make a statement about it. Whereas maximum likelihood will give you a whole bunch of things as being 0, which are of course not true. But they have ways of, they have ways of estimating uncertainty too. So I'm not being completely fair, but yes, questions.
So you're getting back a distribution over two numbers, or is it a?
Yeah,
you're not getting back just like 50-50 or your 90.
No, you're giving a distribution over these
probabilities.
probabilities.
Over P's and Q's.
Yes, yeah. Over these probabilities.
That's what this is giving you versus saying, let's assume we have a fair coin.
Right, yeah. I think this will be clear once we get through the examples, but it is it's a distribution over these probabilities. Yeah.
I guess I think this makes sense, but just checking on the last line of the project there.
Yeah.
So the P of X given Q isn't actually influencing the probability because the exponent there is 0, right? If we're setting it up as
Right. It makes it uniform in this case. Yeah. All right. So I think this will become clearer once we go through the example and do some sampling. So in Campy, the way that you set these things is basically there's a infer EM, which is assuming you have a particular model topology. And so in this case, the biased coin thing that I defined, I feed that to it with no data. And so basically it represents this distribution over the probabilities. You can say, and so analytically I know that the expectations, so these are averages with respect to that distribution, are equal to these things. And there'll be similar things for all edges if you had many, many states. So it's the number of times you've seen the state over the number of times you've seen the state and produced a 0 gives you the probability of seeing a 0 given Q. So this pattern holds through all of them. Okay, and so now we get to what I think will clear up some of these questions. And so what I'm going to try and do is describe the uncertainty that's from the prior. And so this is how you actually do this in Campy. And basically what I'm going to do is just generate 2,000 samples from the prior. I'm going to sample probabilities that are from this prior and say, what is the average? What are the quantiles that give me 95%? So that's what I'm doing here is I have an empty list and then I go through a loop 2,000 times. This particular thing says generate sample, and what I actually get back is a start state, which doesn't make sense now, but will when we get to the next example, and a particular machine. So it actually gives me back a machine with particular values for probability of 0 given Q and probability of 1 given Q. Because this is just the prior, these will vary from anything between 0 and 1, subject to the constraint that they sum to 1. Okay? And so I extract the probabilities here, add them to the list, and then this last part here is just, let's find the average of the samples, and then let's find the quantiles. So 95% of the samples are between these two values. And what we end up getting is the expectation is 0.49. And of course, this is how good this is as a function of how many samples I did. So if I did this 10,000 times, it's better. And then the credible interval is 0.027 and 0.972. Really, if you do lots and lots of samples, it would be 0.025 and stuff. So basically, this is saying that our information about probability of 0 given Q is completely uncertain. It's anything between 0 and 1. Okay. Okay. So now moving on to actual, now we have some data. We're going to change what we know about the probabilities. And to do that, we actually have to do this integral. So, and this is another reason for choosing the conjugate prior, is that you can do this integral. In many, many cases, you cannot do this analytically. And so, I mean, in some cases, they'll call this like the partition function problem. So this ends up being very much like a partition function from statistical physics. But in this case, we can actually. And so this is actually the expression for the probability of the data given that. So we have a whole bunch of these gamma functions, which are n minus 1 factorial. And so the thing to notice here is that basically we have this term which was the normalization from the prior, and then we have something that looks very similar but just flipped over, which now has both parameters from the prior and the data. So we have the number of times q was seen and the number of times qx was seen. And this will end up going into the denominator of Bayes' theorem. This will cancel out with the term from our prior, and this term will flip over, and we'll end up with something that, again, is just a beta distribution. Okay. So again, Bayes' theorem, and then the actual analytic form for the posterior, which now is conditioned on the data. And so in terms of just looking at it squinty-eyed, it looks exactly the same as the prior, right? And that's the whole point of the conjugate prior. There's the same normalization term. There's the same requirement that probability sum to 0, or sum to 1, sorry. And then you have everywhere, instead of just alpha from the prior, you have alpha plus data, alpha plus data. So here for states, here for edges, and here for edges. Okay? And so this is another reason why we can think about these alphas as being sort of fake counts, you know, and think about how big alpha q is relative to nq and how much those determine the probabilities. And so if we do the expectations, again, we can do these analytically. So before, when we did these expectations of the two transition probabilities, without the data, we basically just had this part here. So we just had the alphas without the data, but now we've added those two things in. And of course, these are done in such a way that you can add these and get 1. And the way that you do this in Campy is to now just generate some data. So in this case, I'm going to generate just 200 simples. So I'm not going to give it a lot of data, but I'm going to give it some data and feed it to the Infer EM class, which I give it the structure and I give it the data. And given that both of those are passed to the method or to the class, it will know that this is a posterior distribution rather than a prior, because you're giving it data. And basically what it does is it goes and it counts as the edges. And so we can do the same thing, is let's sample from the posterior. So this is exactly like what we did with the prior, but now we're doing the samples using the posterior we just generated. And so again, now we have a distribution over probabilities that take into account our prior settings and our data. And so this distribution will be different than the prior because it's modified by the data. But the idea is exactly the same. We're to sample through each time we sample a machine, the start node, we extract the probability, add it here, and then we just look for the average, and we look for the credible interval, which we've made 95%, but it could be whatever you want it to be. And so here you get an expectation of 0.103. And if you remember the way I defined it, it was 0.1, so not so bad. But for this amount of data, you would expect this not necessarily to be always that accurate. And that's kind of reflected by the fact that our 95% credible interval is between 0.6 and 0.15. So there's actually still a fairly large uncertainty in this. And so we can actually plot this and get a sense. So I'm trying to make this really, really practical so that, like, if you have a data set and you're interested in, you can just go and blast away with this. And so basically all I'm doing here is doing histograms for each one. So I do a histogram for the samples that I had from the prior. I do a histogram for the samples I had from the posterior. And then I plot them both so we can see what they look like. And they should reflect the kind of things that we were just talking about. So the blue is the prior. And so basically what you can see is that it's basically at 1 all the way across 0 and 1. And the reason that it's not uniform is it's 2,000 samples. It's a 2,000 samples representing a uniform distribution over 0 and 1. These are the samples from the posterior, and the true value is 0.1. So it says something like, you can say a point estimate is the average with respect to this distribution. You can do a maximum. There's also something called maximum a posteriori, so you can maximize these things, but I tend to just use the mean. And then the breadth of this thing is meaningful. It's how certain are you of these things. Okay. So, and then I think where we start getting into the point where the things you've been thinking about in this class is, well, now we have a model, we have some sense of what the transition probabilities are, how uncertain we are, we want to do things like we want to estimate H mu and C mu and all these things. How would we do that? Well, we have distribution of these things, so we really want to take means and have credible intervals for all these things. So we're going to do exactly the same thing we were doing for the transition probabilities, but for any function that you want to. And it's unfortunately not as simple as saying, like, take the analytic posterior mean for the transition probabilities and plug it in to p log p. That doesn't work, unfortunately. Well, I don't know. If lots and lots of data, that's fine. But in general, it's best to at least think about this. And the idea would be that you're going to sample settings for the transition probabilities from your prior or from your posterior. And then whatever is a function of those parameters. So the idea here is that this is a particular setting for the transition probabilities. We plug that into the H mu thing. We get a sample of H mu and repeat this over and over and over again. Okay, so it's a numerical average or a numerical sampling of these functions. So these should look really, really similar. And we'll do it for the entropy rate, for the prior, and for the posterior, just to look at what you might get. So for the prior, now when we sample things, again, we're just getting a machine in a node. But because that's a machine, I can actually just call entropy rate. So I say what it is, get that, and I add it to my list. And then at the end of this loop, I have a list of entropy rate estimations. I find the average, and I find the confidence intervals, or the credible intervals. And we end up getting something that's 0.72, but is anything between 0.99 and 0.078, so quite uncertain. Okay? And we'll plot these in a few slides to see what they look like. And so one thing that this also turns out to demonstrate is that a uniform prior over the transition probabilities does not translate to a uniform prior over entropy rate. So if your primary goal is estimation of entropy rate, that's something to be at least consider and think about. Do the same thing for the posterior, so I won't go through it, other than to point out that we get a different value for the posterior with the 200 samples. And again, yeah, smaller interval, so that's collapsed a bit. And do our histograms. And it looks like this. So this is the entropy rate between 0 and 1. And so if you uniformly sample zeros and ones, or a probability of 0 and 1, you end up getting something that's very, very peaked at 1. And this is actually, I think, something related. You looked at probability densities for iteration of the logistic map, which has this unimoidal shape. So if you have a density that's near the point of 1/2 for logs, it's a slope less than 1 near the center, near probability 1/2 for the entropy calculations. You end up folding. There's a 2-to-1 aspect of this, and then so it ends up that you get squeezed, and so a uniform distribution over over probabilities ends up looking like this when you pass it through the entropy rate function. Okay. And then this is what the posterior looks like. And so the true value for this was 0.46, which was somewhere in here. So it's overlapping, but it also says that it's fairly uncertain. Okay. All right. So I think that's the first example of like a very simple model, a prior, a posterior. You can get point estimates, but there's uncertainty. And of course, these uncertainties reflect how much data there is. If this were 2,000 samples rather than 200, this would be much more sharply peaked. And I think the other thing that's useful to think about is that, in particular for functions of these transition probabilities, if that's the critical thing you're trying to look at, it may be important to understand what the prior says in terms of the prior you set for transition probabilities, how that affects what it says about the entropy rate. So, I mean, it turns out that 200 simples is enough to change it from this to this. So maybe it's not a concern depending on how much data you have, but it's worth considering. Okay. All right. So now on to the meat of the issue, which is dealing with things that you've been studying, epsilon machines and hidden Markov models. So I'm going to start off with a couple of definitions just to ground what we're doing relative to what you've already seen. And I'm going to restrict what kind of hidden Markov models we're looking at. So just definitions, and I think these should all just be familiar with you, for you. So a finite state edge-labeled hidden Markov model consists of a finite set of hidden states, a finite alphabet, and then the set of transition matrices for each output symbol. And if you want the state-to-state transition matrix, you can sum all of these things. So it's a hidden Markov model that's unifilar. Well, I'll say unifilar in the next time, but in this case, it doesn't say that it has to be unifilar, but we will restrict that next. But it's an object very much like golden mean, even process that you've already been dealing with. Okay. So a finite state epsilon machine has additional restrictions on it. So it is a finite state edge-labeled hidden Markov model, but it requires unifilarity. And just a reminder, so for each state and each symbol, there's at most one outgoing edge that has output symbol X. And this turns out to be absolutely critical for what I'm doing and why I can do it analytically, because I can then assume a start state and make trace through the machine and actually count edges. So this will, what I'm going to be talking about, can't be done for general hidden Markov models where there are multiple edges that produce a 0 going out. Then you can't do this uniquely. But so we're going to require unifilarity. And then for an epsilon machine, we want the states to be probabilistically distinct. So there'll be some word for each state that's different, given that you start on K and J for every pair of nodes in the machine. For what I'm doing necessarily, I'm not necessarily so concerned about whether or not it satisfies this and is actually an epsilon machine in terms of the inference. That's for later. You can test and see whether or not what you get is something that actually obeys this. But this could be just a unifilar hidden Markov model. It doesn't have to be minimal. So you can give it any structure and it will still work. So I'm going to require this in what I'm doing. This, in terms of saying that it's an epsilon machine or not, is something to be tested at and look at. Okay, so how do we actually do the edge counting? So we've seen the fair coin model, and we're thinking about counting edges and counting state transitions. Now, how do we handle hidden states? And so the basic idea here is we assume this particular structure. We have some data that starts with these particular series of symbols. What edges were used, how many times, what states were visited, how many times. So really, really simple. Unifilarity saves us, because we can actually then just test this out and say, well, okay, if we assume that the start state is A, I can do, let's see if I can do this correctly. If we start in state A, we do a 1, the next symbol is a 0. So the idea of the counting is that we have a start state that is before the first symbol, and then we look at what is the next thing. So I assume start state A, I see a 1, I go here, the next symbol is a 0, there's no edge with a 0 here, so I know this absolutely cannot be the start state for this thing. Right? So it's really, really simple, not complicated at all. But if we use B, well, we can do B, we see a 1, we see a 0, we see a 1, we see a 1. Right? So we know exactly, if we assume start state B, what path was taken through here. And we know how many times we saw B, how many times we traveled this edge versus this edge. And so basically we're going to add an extra level of inference in that we're going to do inference many times, assume this start state, do inference of transition probabilities if possible. So in this case, it's not possible because the likelihood of the data is absolutely 0. It can't happen. Whereas in this case, it's actually non-zero. So we would do it just for this case. And so for more larger machines, this is going to end up being something where you do each of the 5 states in a 5-state machine. Okay. Is that all clear? Yeah. Okay. So I mean, it's really, really simple. How to handle it is builds on what we've done already, but I think the basic idea of how we get the counts is really important. And again, it's critical that we're unifilar structures. We couldn't do that counting if it weren't unifilar. So like we can't, if you feed SNS to my code, it will say ACK, non-unifilar, and it will just throw an exception. And that's because it can't count this way. So now we're going to do inference, but we're going to assume a model structure and an assumed start state. And so you could almost think of this as a bunch of different models where you have a model and you assume start state A is one model, and you have a model or structure and start state B is another model. And then we're going to do model comparison to choose which one is which. And as I've been saying, you have to do this for every start state in the machine, at least try it. And some subtle issues that end up coming in terms of what we're doing here, in particular when we get to the next lecture, which is dealing with this library of candidate topologies. There's things that are periodic structures. So you have 5 states and it just goes along the 5 states. All of the probabilities are 1 by definition. There's nothing to infer. So these things are either probability 1, like likelihood is 1 or 0. And a typical machine is some combination where there's some states that have probability 1 going out and some that have 2 edges or 3 edges. It depends on the alphabet. So I actually end up having to divide the set of states in the machine into a subset or a potential subset that has more than 1 outgoing edge. So there has to be at least 2 edges going out so that I actually have to infer what the probability of taking edge 1 versus edge 2 is. Other ones I don't worry about at all. So in this case, when I'm saying theta I, I'm looking at just the subset of states that have more than 1 outgoing edge. And I'm only inferring those. The states that have 1 outgoing edge are still important because they're basically like a filter. They can be, they can say the probability is 1 or 0. I mean, every time they hit that state, they have to have that symbol and go in a particular way. All right, so how do we do that? So this ends up being why we write the likelihood this way, is kind of for this issue. We end up with something that looks very much like our biased coin before, but now we're doing products of them for every state and every output symbol. We have the probabilities, given state, output symbol, and this is the number of times you've seen state symbol given that we assumed start state A or B. Or it could be 0, like in one of the cases that I just showed, where there's just the path is not possible. So you basically get these 2 forms. And we get edge counts, state counts. Will end up being, I'll use this little bullet thing to say that we've summed over all outgoing edges. And yeah, likelihood can be 0. And so now we have the prior. And so this is part of the motivation of doing the simple biased coin, is that we end up with something. Now, if you take away this product and the things here, I end up with something that just looks like the beta or Dirichlet distribution for the fair coin. But now I have a product that's for each of those S star states, the ones that have more than 1 outgoing edge. And the fact that these are just products is reflective that there's independence conditioned on these states, right? But for each outgoing state, you have a distribution. So a distribution over probability, transition probabilities outgoing for going out of that state. They have to sum to 1, and they all have to be normalized to 1. So however many outgoing edges, or however many states you have with more than 1 going out edges, is a product of those many beta or Dirichlet distributions. And again, we have these alpha parameters, which again are just like what we had for the biased coin, right? So this is like putting in an artificial count for seeing that edge. And so this would be set to 1 in general and can't be. That gives you uniform over the simplex conditioned on that particular state. So you end up with bunches of uniform distributions over transition probabilities conditioned on each state and the product of all of those things. Okay. And yeah, okay, so that's what I'm saying here. And we, again, have an analytic expression for the transition probabilities given the prior, again, is just this alpha state symbol versus alpha state summed over all the symbols, which I was tempted to write 1 over the size of the alphabet, but that's not always true. In these cases, you could have a state that has, it's 4 letters in the alphabet, only has 2 edges going out, so it might not be 1 over A. And then if it's not things that you're inferring, you're going to basically have, by the topology of the machine, certain probabilities that are just, and probably I shouldn't put it as an expectation with respect to the prior, but just emphasizing the point that some probabilities are just 0 or 1 by definition of the topology. They have 1 edge going out of the state. All right. And so again, the beauty of conjugate stuff is this is the evidence term, this is the normalization or the partition function. You can actually calculate these things. And again, we have the term from the prior, we have the term from the posterior, which is flipped. So here we just have the alphas, here we have the alphas plus the actual counts. This will end up canceling out. And we end up with the posterior, which looks just like the prior, but with alphas replaced by alpha plus n's. So you have these things here. Okay. And so as you would expect, we know analytically what the posterior expectations are. Again, it's just prior parts plus data parts. And always in the back of our mind that these things only make sense if there was actually a valid path through the machine, assuming the model and the start state. Okay. Otherwise, basically, the likelihood goes to 0, the evidence is 0, the posterior is just not defined. All right. So what about that annoying start state? One thing to keep in mind is that because of unifilarity, when we infer the start state, we've actually inferred the whole hidden state path. Right? Because if you know the start state, and it's a unifilar machine, you have observed data, there's a unique path through there. Or there's either a unique path or there's not a path. Right? That's only because it's unifilar. So the start state seems annoying, but is actually, I mean, potentially, depending on what you're applying this to, might be quite interesting. If the hidden states are something that's important and knowing which way you go through them is valuable, it's actually quite good. But we're going to want to, or we have to, in terms of being able to compare topologies and ignore things that we're uncertain about, like start state and transition probabilities. We have to sort of integrate out this uncertainty. And that's what we're going to try and do now. And so we're going to apply Bayes' theorem again, but at a different level. And so the denominator of Bayes' theorem when we were inferring the transition probabilities was this normalization term, which is probability of data given the start state in the model. We've averaged over the uncertainty in the transition probabilities. And so the one thing that I do is this looks very much like a likelihood, right? When we were, the very first one we saw, this was probability of B given transition probabilities given model. Well, this is now just a likelihood probability data given a start state in a model. We've integrated out the uncertainty of transition probabilities. And we're going to treat this as a likelihood and build another level of Bayes' theorem on top of it. How do we do that? We end up, so there's a cost when every time you do Bayes' theorem. You have to have some statement prior about the thing that you're trying to infer. So here's this thing that came from inferring transition probabilities. And what we want is the probability of the start state given the data and that, the model topology. But we have to introduce a probability of the start state given the model, which is our prior statement about these things. And then we get this term in the bottom, which sums basically the numerator over all possible states. Okay. And by default, in Campy, what ends up happening is this ends up being set to 1 over the number of states. So I know that people have commented, why don't I just set it to the asymptotic distribution? And the point is that we don't know the transition probabilities. I mean, you could say statements about, you have to think of this as being a topology and being completely uncertain about the transition probabilities. So really, it turns out actually that the asymptotic distribution will be reflected in this thing often. So it's backwards to the way that you're used to thinking about it. So the idea here is to think about, we have a structure, we don't know what state the machine was in when it started generating data, and we just want to figure out which one it was. And we're going to start off with a prior assumption that we don't know, all of them are equally likely. And then we're going to use this term, which gives us influence of the data, to determine which one is the most likely. Okay, so now an example to ground all this, and hopefully it will all be clear. All right. So even odd process. Again, this is Campy stuff, so I write a string up here, and I've made the even odd process a little bit strange. If you just say even odd from Campy machines, you'll end up getting 50-50 here and 50-50 here. And again, I just changed it to be clear that I'm not just, the prior isn't just reiterating that. Because the expectations will look exactly like the machine, and that I think is confusing. So I'm going to be generating data with something where these probabilities are the ones that are generating the data. This is what I'm actually using. Okay? And so I create the actual machine, and then this thing is just printing this out here. I guess on Sage you just do a normal draw. And then another thing to look at is here I can demonstrate the difference between, here's the set of all states, so A, B, C, D. Whereas the ones that actually have more than one outgoing edge are just A and C. So this has 2 outgoing edges, and this has 2 outgoing edges. Whereas D, that's 1 by definition. B is 1 by definition. So I don't have to infer anything about those. Those might make the likelihood for a given start state 0, but I don't actually have to infer the transition probabilities. Okay. So again, I'm going to go pretty much through the same kind of things that I did with the fair coin, but I want to be a little bit more careful to demonstrate the figuring out what the start state is and what actual edges are being traversed. And so here again, using the exact same code, now I feed it the EO machine. That gives me a prior because I didn't give it any data. The machine, I'm actually going to set the current node to A. So it's going to be in state A. So the data is going to start generating from here. We're going to see what the actual code gives us back. And then the data that I'm going to generate, it turns out that this symbols iter, if you actually want the machine to update the internal state while it's generating the data, you want to use this rather than symbols. So each time it's generating a symbol and I'm adding it to the data, this EO machine is updating its internal state. So I can then print this out at the end and say, after the 200 symbols that I generated here, it was in state A again. Okay. And then we're also going to create a posterior. So the same as the prior, but now we're giving the machine and the data. And yeah, this just prints out what the last state was. So this code is basically just trying to say, what are the probabilities of each of the start states, and what is the state path? And so this is for the prior, where there's no data, so it just doesn't have any information about it. So I'm just giving you an idea of what to expect when you do this. And on the Sage worksheet, there's a method that's called summary string when you have a prior or a posterior, which spell out a whole bunch of information. So you'll be able to see that, but it just doesn't fit nicely on slides. So this is to give you an idea of what's going on. But the idea here is probability of each of the start states a priori is equal. So it's 1/4, 1/4, 1/4. We have no information about the start state. There's no information about the last state. And so a lot of the Campy code will just spit back none or empty lists if it's a prior, because there's no information to be provided for these particular things. Now, if we do this for the posterior, we get something different. And so we get the probability of start state A, which we know was the true one, because we set it, is actually less probable than start state D. But then we can actually print out the state path. If it was the start state was A, it started in A and then it went C, B, A, da, da. This one with start state D is also possible given the observed data, and it goes DC. One interesting thing that's very common in this inference thing is these first 2 symbols are different, but everything else is the same, right? And the last state is the same. So the paths in terms of the edge counts are actually very, very similar. This is not always the case, but often is the case. And so if we go back to the thing, we can actually get a sense of why A and D might be common things. So one thing is that this is a high probability, so almost certainly the data went this way, 1 and then 0 or something like that. And so D also has a probability of a 1. Both of these have high probabilities. So the data is almost certainly something that went 1, 0, or 1, 1, and you just can't tell the difference between these things. And then the relative probabilities of the 2 start states actually ends up being the fact that both of these are possible, but this is a transition probability of 0.9 and this is a probability of 1. And so it's actually just reflecting that fact. So they're almost the same, but not quite. Okay. And given lots and lots of data, you would never be able to tell, unless I told you, whether or not it was A or D, given this inference. But in each case, so for the posterior, we've ruled out state B, we've ruled out state C, and we have state A and we have state D as possible, and we can infer transition probabilities and all these things from them. And so here's very compact code. What we're going to do all on one slide is we're going to infer, we're going to get samples for H mu and C mu from both the prior and the posterior, and then we're going to look at plots of them for this particular thing to give you a sense. I'm not going to worry about the transition probabilities, but just the functions at this point. And so here we have, again, we're going to do 2,000 samples, and then each time through, we do, for the prior, we generate a sample. We get, from that sample, we get H mu, we get C mu. We add them to their respective lists for the prior, because we use the prior here. Here we have samples from the posterior. We get the entropy rate, statistical complexity. We add them to the respective lists. So this creates 2,000 samples of H mu and C mu from the prior and the posterior for this even-odd process. So what do we get? Histogram plotting. So the first thing is entropy rate, and this is the same kind of thing where we end up getting blue is the prior. And so one thing that's interesting about a lot of things that, and we'll see this again in the looking at structure, is that for the fair coin or biased coin, that actually could have entropy rates all the way between 0 and 1. But when you start having structure and restrictions and all these things, very often the maximum entropy rate is actually much less than 1, even for the binary alphabet. So that's something that we see here, is that if you just sample uniformly from the transition probabilities, you end up getting a distribution that looks like this. And again, it's not uniform, even though our distribution over the transition probabilities was uniform. And then the posterior looks like this, and the true value is 0.43. So again, it captures it. And this is kind of deceiving. I mean, we'll see that it's not always deceiving. I mean, we're doing data from a known source and inferring probabilities from a known source. The next thing is we're going to actually have to infer what was a structure and then do all of these things on top of it. But what comes next critically depends on everything that we're doing today. Is all of this underlies the model comparison at the higher levels. And all of the uncertainty that we have here in terms of start state and transition probabilities is still there when you're doing model comparison. So you still want to reflect that if possible. Okay. And then for C mu, same kind of thing. C mu for the prior ends up, it can be between 1 and 2 bits. The posterior ends up being here, which I think is pretty good for the true value. And again, what I'm not doing here, but what you could do is you could take those lists of samples, find a mean, find credible intervals using quantiles, like all those kind of things. It doesn't have to be just a histogram. So you can actually get a number in terms of like, what is the mean of the entropy rate with respect to the prior? You're probably more interested in what is the mean of the entropy rate with respect to the posterior, but it's good to think about both, just to see what's happening. Okay, and then the very last thing for today is each of those samples was being taken, so maybe if I go back to here. So when I was doing these things, I was sampling one machine from the prior, and I was getting its entropy rate. So this has particular transition probabilities. I was getting a specific entropy rate and a specific C mu for that particular setting of the transition probabilities. So these things are correlated, and they reflect the structure of the even-odd process. So if I plot H mu and C mu in the same plane, I'm getting the joint density over H mu and C mu for the prior or the posterior. And so that's what this last slide is. And you'll see a lot of these in the next time because they're quite interesting. And so what this is H mu and C mu. The blue is the prior, so you're sampling uniformly over transition probabilities. And you can see there's a kind of structure here which is reflecting sort of moving one transition probability between 0 and 1 And it depends on which edge, and you move through all these things. And this is, again, 2,000 samples if you want. Do 5,000 more, or however many. It's all a matter of computer time. And then the green is what you get if you restrict the transition probabilities on the data that you've observed. So this is how restricted you are given that you've seen 200 samples from the even odd process. And I haven't even, so this notice wasn't even, I wasn't concerned with what the start state was. Right? I just took the samples, and each time the start state was potentially different. It would have to be A or D, but it was giving me these values. And so it's giving me this right value, and it basically 1.84 is the right one, and then 0.438 is that. And so if you give it 2,000 samples instead, you end up getting something that's even more sharply peaked. Okay. And so that's my last slide. So.